So far, we've looked at the partial derivatives to tell us the slope of a function in the x and y directions. But there are lots of other directions besides horizontal and vertical. So we're going to develop the concept of a directional derivative, which is the slope of a function in any direction. When we took the partial derivatives, we were using a step size of h in either the positive x or y direction, and then let h go to 0. We're going to do the same thing, except free ourselves up to move in any direction. If u is a unit vector that we write as u1, u2, then we can multiply it by h to get a vector of length h. And this vector shows us the change in x and y if we take a step of size h in the direction of u. Then the directional derivative is just the limit of the difference quotient as h goes to 0. Definition. Let f of xy be a function. The derivative of f at the point xy in the direction of the unit vector u is denoted as d sub u of f of xy, and is given by this formula for those values of x and y for which the limit exists. D sub u of f of xy is called a directional derivative. This gives us the slope of a function when moving in the direction of u. There's not too much to say about this formula, as it's just a difference quotient using a step size h in the direction of u. One important element to remember is that u needs to be a unit vector for this formula to be correct. This formula is a little more difficult to work with because we are changing both variables at the same time, so we're going to take a more careful look at it. Suppose we have a function f, and let's fix a specific point x0, y0 and a specific vector u1, u2. To get the directional derivative, we're going to focus on the line that passes through the point x0, y0 whose direction vector is u1, u2. Here's the parametric form of that line. Notice that we now have a situation where we can apply the chain rule. The function f depends on both x and y both x and y depend on t. Furthermore, the derivatives of x and y with respect to t just give us the constants u1 and u2, and this means we have a formula for df dt. It turns out that u being a unit vector means that we are moving along the line at unit speed, and this corresponds exactly to the directional derivative. The justification for this can be done algebraically, but it's more intuitive to observe that this concept of unit speed is what we use for partial derivatives in the x and y directions, and so this is the natural way to generalize it. Again, it's important that we are using a unit vector in this formula. If you are working on a problem where you aren't given a unit vector as the direction vector, you're going to have to divide it by its length to turn it into a unit vector before doing the calculation, otherwise you'll get it wrong. If you look at the formula for the directional derivative, you might pick up on the fact that it looks like a dot product. Specifically, it's the dot product of the vector of partial derivatives with the vector u. This vector of partial derivatives turns out to be an important and useful value in calculus, so we give it a special name. This is known as the gradient of f, and it is written with this upside down triangle. The symbol is called a nabla, but it's often just called del. So the gradient of f, or del f, evaluated at the point x0, y0, is the vector of partial derivatives evaluated at the point x0, y0. Notice that we've put a vector symbol over the del. As always, this implies the result is going to be a vector, but there's more to it. The del notation is sometimes treated like an operator, so del is the vector of partial derivative operators. This is a handy notation because it means you can now imply formulas using vector operations. For example, if you have the vector function f equals f1, f2, we can write del dot f and come up with a meaningful interpretation of what this calculation is supposed to be. This is actually known as the divergence, and it's a concept that's important when working with vector fields, which is a topic that's sometimes covered in multivariable calculus, especially if you're on a physics or engineering track. The del operator generalizes to 3 or more dimensions in the way you might expect it to. If our independent variables are x, y, and z, then del is the operator where the partial derivatives are with respect to x, y, and z. We're not going to go into all the details and nuances of this notation, but if you go on in mathematics, operators become part of the language you use to describe math, and you will become more acquainted with the ideas at that point.